You know, for almost 100 years, Schrödinger's cat has been the perfect, if slightly morbid symbol for just how weird quantum mechanics really is. It poses one of the biggest questions in physics. How do you look at something without completely changing it? Well, coming out of Tehran, a new proposal suggests maybe the answer isn't to look, but to listen.
And yeah, that question really boils down to this. If the very act of peeking into a quantum system forces it to make a choice, to pick a state, how can we ever know what it was doing a split second before we barged in? It feels like an impossible catch-22.
So, you've got this cat, right? It's in this bizarre state of being both alive and dead at the same time, a quantum superposition. That is, until the moment you measure it. But what if there was a way to peek inside that box without forcing its hand? That's the absolutely electrifying idea in a new proposal from Dr. Reza Rizii Kanga at Shahid Rajeh Teacher Training University. His work lays out a path to finally probe the cat's true state. But to see why it's so brilliant, we first have to understand the problem it's trying to solve.
To really get why this new idea is such a game changer, we have to look at the old way of doing things. Why is just looking so destructive to a quantum system?
Well, it's all because of something called wave function collapse. See, when we do a direct, strong measurement, we're not just being a passive observer. No, we're smashing into the system, we're interacting with it, and we're forcing it out of that beautiful, delicate superposition. We're essentially yelling at it, pick one, and all that crucial quantum information we wanted to study, poof, it vanishes in that instant.
So how do you get around that? If shouting at the system breaks it, the new proposal says we should try something else entirely. We need to learn to listen. The whole idea is to use a gentle, non-invasive probe. Think of it as a quantum whisper instead of a destructive shout.
And the process itself is just beautiful. You take a probe particle, say a neutron, and you send it through the box. Now, it's not carrying enough energy to force that wave function collapse, but the encounter does something incredibly subtle. It ever so slightly alters the neutron's own quantum properties. Specifically, its wave function gets a tiny phase shift. You can think of it like a tiny delay in its journey. That delay is the secret message, the whisper of information we're trying to decode. You know, the method is so sensitive, the paper even suggests that cosmic background radiation could, in theory, act as a similar natural probe, constantly whispering to systems all around us.
Okay, so this is the really clever part. A neutron comes out carrying this secret message. How in the world do we read it? This is where we turn that super subtle interaction into cold, hard evidence.
The magic is in what's called a state-dependent phase shift. Here's what that means. The mass distribution inside that box is slightly different if the cat is alive and breathing versus if it's, well, not. That tiny difference in mass creates a tiny difference in gravity, which ever so slightly alters the neutron's path. That's what creates the phase shift. It's an encoded message telling us whether the neutron just flew past a living system or a dead one.
Okay, so let's play this out. We send thousands of neutrons through the box. If the cat inside were definitively 100% alive, those neutrons would create a very specific interference pattern on a detector screen. You can think of it like a clean fingerprint for the alive state.
And you guessed it, if the cat were definitively dead, the neutrons would create a different, physically shifted interference pattern, a second, totally unique fingerprint for the dead state. So we've got two clear outcomes, two distinct patterns. But what happens if the cat isn't one or the other? What if it's both?
And this, right here, is the smoking gun. If that cat is truly in a superposition of both alive and dead, the pattern we get is a blurry, beautiful combination of both of the other patterns. We are literally seeing the fingerprints of two realities overlaid on top of each other. This isn't just noise or ambiguity. It is a direct physical signature of a macroscopic quantum state. It's incredible.
And this isn't just a pretty picture. It's backed up by some serious math. The core formula in the proposal shows the probability of that neutron landing at a certain angle. The first two parts you see here, those are basically the patterns for alive and dead on their own. But that last piece, that cosine term, that's the interference term. It can only be there. It literally can't be anything but zero unless both states exist at the same time. That's the mathematical proof of superposition, right there.
Now, of course, a single neutron's whisper is way too faint to hear on its own. This is fundamentally a statistical measurement. To be sure you're seeing a real pattern and not just random noise, you need a crazy high signal-to-noise ratio. We're talking about sending thousands, maybe millions of neutrons through the system one by one, to patiently and meticulously build up these patterns until the result is undeniable. So, Okay, we've done the experiment. We see this blurry, combined pattern. We have the data. What does it actually mean? This is the point where the experiment dives out of pure physics and right into the deep, murky waters of philosophy. It forces all the different interpretations of quantum mechanics to put their cards on the table. Right, so the classic Copenhagen interpretation would say, look, that pattern is just a wave of probabilities. The cat isn't really both until a final, strong measurement forces it to be one or the other. The many worlds interpretation is way bolder. It says both the alive and dead universes are equally real, and our little whisper probe is picking up the shadows of both of them existing at once. What's also huge is that this kind of result would support decoherence theory, the idea that quantumness gradually leaks into the environment over the idea of a sudden magical collapse.
But there's one interpretation, cubism, that this experiment puts right in its crosshairs. Quantum Bayesianism, or cubism, basically argues that the wave function isn't a real thing out there in the world. It's just a mathematical tool that represents our personal beliefs about a system. This experiment is a direct challenge to that. We are measuring a real, physical phase shift that's been encoded onto a real particle. It's an objective property of the universe. It's not just an update happening in our brain. It's physical evidence for a reality that exists whether we know about it or not.
All right, this all sounds mind-bendingly cool, but let's get practical. We're not actually going to put a cat and a vial of poison in a lab with a neutron beam. So how do we take this brilliant thought experiment and turn it into something we can actually build and test?
We build a modern-day stand-in. Instead of a cat, we use a Schrödinger box simulator. What this is a system with a superconducting qubit, the same thing that powers a quantum computer, and we couple it to a tiny, cooled mechanical resonator. This resonator is a macroscopic object, big enough to see, that we can actually put into a genuine quantum superposition of two different states. It's the perfect mimic for the alive and dead conditions.
Now, this is not a weekend project. There are major engineering hurdles, and we have to be realistic about what's hardest. Number one, right at the top of the list, is just preparing and maintaining that incredibly fragile macroscopic superposition in the first place. Any tiny vibration, any stray heat, what we call environmental decoherence, can destroy it in a flash. After that, you have the massive challenge of gathering enough data for a clean signal, and finally, your neutron detectors have to be ridiculously sensitive to pick up these tiny shifts.
But this isn't science fiction. The author actually lays out a concrete plan. Using superconducting qubit technology that already exists, a project like this could realistically go from design to its first data runs in about 4 years. From an experimentalist point of view, this is the exciting part. The neutron probe is really hard, but it's achievable. That other idea, using cosmic radiation, conceptually amazing, but the engineering challenges are just, well, they're astronomical for now. The focus has to be on what we can build and test today. And really, that's the whole point. For so long, the measurement problem has felt more like a late-night philosophical debate than a question for a laboratory. This proposal turns that completely on its head. By giving us a clear, testable physical signature of a macroscopic superposition, it lets us sidestep the endless arguments and actually get hard data on one of the deepest mysteries there is. It's about making the unobservable observable.
So in the end, this whole proposal is like a direct message to Schrödinger himself. It's saying that time for just thinking about the cat paradox is done. As the quote puts it, the thought experiment is over. It's time to get to work in the lab. The paradox is no longer just a weird story. It's an empirical question. And it forces us to ask even deeper questions. Does this experiment point to an objective reality that exists without us? Or is reality itself fundamentally relational, only defined by how things interact? We finally have a blueprint to gently, quietly peek inside that box and see what we find.